This video will focus on Section 2 from Chapter 7, where we will really get in and understand the concept of the sampling distribution. The sampling distribution is the basis for everything that we do for the rest of this semester. Determine the mean and standard deviation for the sampling distribution of x bar. That will happen in this video, and we'll also use it to calculate probabilities associated with the sample mean. We will also learn about the central limit theorem, how important it is, and where to apply it. The sampling distribution is the distribution of the probability of all possible values of a statistic for a given size sample selected from a population. So the sampling distribution really is about all of the possible values of a statistic, like all the possible means that you could get when you're sampling from a population with a given sample size, and the associated probabilities of each of those sample means occurring. So we're going to walk through an example here to help you understand the concept of sampling distribution. Assume that there's this population of only 4 people: Mr. Cheesy, Hot Pink, the Blonde Gal, and Mr. Frumpy Pants. Suppose the variable that we're interested in is age. So we know the values of the ages here. Mr. Cheesy's 18, Hot Pink is 20, the Blonde Gal's 22, and Mr. Frumpy Pants is 24 years old. Okay, we could talk about the distribution of the population. So we've got ages 18, 20, 22, and 24. Each of those has a 1/4 chance of occurring, or a 0.25 chance of occurring in our data set. We could also easily calculate the average age in the group, add them all up, divide by 4, we get the average age of 21, and we could calculate the population standard deviation of 2.236. Now, to get to the sampling distribution, we'd actually be having to take samples and calculate an associated statistic. So consider all possible samples of size 2. So we've got the first observation and the second observation. We've got our ages 18, 20, 22, 24. Pretend we've thrown those in a hat. We could draw any one of those out at random. And then in the second observation, we've thrown back in whichever number we drew out. So we still have the chance of getting 18, 20, 22, and 24. We're sampling with replacement. That's what that's called. So we could get 18 and 18. Our first observation would be 18. Our second would be 18. We could get 20 and 22, so we could have 20 as the first observation, 22 as the second, 24 and 20, and so on. So you see there are 16 possible ways that we could draw 2 ages out of the hat with replacement. To move from the yellow table here on the left to the teal table here on the right, we've simply calculated the average value, the statistic, for each possible sample. So if we average 18 and 18, we get 18. If we average 18 and 20, we get 19, 18 and 22, we get 20, and so on. So you see all of the possible sample averages that could exist given our samples of size 2. To turn that into the sampling distribution, we simply convert the information in the teal table into a graph. There's one way out of these 16 possibilities that we could get 18. There's a 1/16th chance of getting the average of 18. There's 2 19s, so there's a 2/16th chance of getting 19. There's 4 21s, so there's a 4 out of 16 chance, or a 25% chance of getting 21 as the average, and so on. So we see the distribution of all of the possible sample means that we could get and the associated probabilities. This is a sampling distribution. It lists out all of the possible means and the associated probability of each of those means occurring. Notice that that's no longer a uniform distribution. In fact, it starts to look a bit bell-shaped. We could calculate the average for all of those means. Notice the new notation. The mean of the sample means is 21. The standard deviation of all of those sample means is 1.58. Okay, here's the side-by-side comparison of the population itself. We see each of the 4 individuals here. The average was 21. The standard deviation was 2.236. For the sample means and their distribution, the average was also 21. The average of all the averages is 21. But the center of the distribution for the population is 21. The center for the distribution of the means will also be 21. You'll also see we have listed here that standard deviation of all of these means is only 1.58 compared to 2.236 for the population. The standard deviation of the means is smaller than the standard deviation of the individual population values. The reason that happens is to get these individual values of x bar, we've actually had to average a couple of values from this population distribution over here. If we're taking any two values from the population and averaging them together, those two values averaged together are more likely to be close to the center of the distribution than an individual value of the population itself. So the spread of those means will be less because we're averaging together individual values from the population. A couple of theorems from the textbook. Theorem 1 says that for any population, the average value of all of those sample means computed from the random samples of a given sample size will be equal to the population mean itself. The average of all the sample averages is equal to the population average, and that means that this is an unbiased estimator. Also, for any population, the standard deviation of all possible sample means computed from all random samples of some particular size is equal to the population standard deviation divided by the square root of the sample size. So we see here the standard deviation of all of those sample means is equal to the population standard deviation divided by the square root of the sample size. That's theorem 2. Theorem 3 really says that theorems 1 and 2 apply to the normal distribution. And we have an interesting fact that we'll learn more about later. As the sample size increases, the sampling distribution itself becomes more normal. So this idea of unbiased from theorem 1 tells us that whatever the population mean is, that will also be the mean of all of those sample means that we could get from that distribution when we have a given sample size. So the sampling distribution has the same mean as the population distribution. The sample mean is a consistent estimator. What that means is, as our sample size increases, the value of the x bar becomes closer to the value of the population mean. In other words, our sampling error gets reduced as our sample size gets bigger. Notice that we've got our original population here in the green, and as n increases, or as our sample size increases, the standard deviation of that sampling distribution gets smaller and smaller. So the sampling error that we could get will get smaller. We're more likely to be close to the true population value. We can calculate a z-score for our sample mean, just like we do for an individual value of a random variable. That z-score should look familiar to you. Before, we would have placed x here, x being some value of the population, and subtracted out the mean to figure out how far away from the mean that individual x value is. Now what we're going to do is say how far away is the sample mean from the population mean. Or really, that's our sampling error on the top. The denominator before was just the standard deviation of the population distribution. Well, now the denominator is the standard deviation of the sampling distribution. So we've got how far away is this mean from the population mean, or our sampling error, divided by the standard deviation of the sampling distribution. So we're really measuring how many standard errors this sample mean is from the population mean. If we have drawn a relatively large sample from the population, in other words, our sample size is more than 5% of the population size, and we did that sampling without replacement, we really have to make a small adjustment to our z-score here to make that z-score be accurate. So this square root of the population size minus the sample size divided by the population size minus 1 is our finite population correction mechanism that we use to correct the z-score. So let's run through an example of how we would apply this sampling distribution idea for the mean. Suppose that we have a population that's normally distributed with a mean of 1.5 and a standard deviation of 0.05. We've collected a random sample from the population. We get the numbers 1.57, 1.59, and so on. The first thing that we should do is compute the sample mean. So the sample mean is the sum of all 8 of those numbers, which is 12.52, divided by 8, we get a sample mean here of 1.565. We need to define the sampling distribution for x bar. So what is the mean of all of those sample averages? Well, the mean of the sample averages is the mean of the population. So that's 1.5. The standard deviation of all of those sample means is the standard deviation of the population, which is 0.05, divided by the square root of 8, because 8 is our sample size. We had 8 individual items in our sample. So the spread of the sampling distribution is 0.0177. Now we need to define the probability statement of interest. What is it that we're trying to find the probability of? And I always say, draw a picture. So suppose we're interested in finding a sample mean, notice x bar, of at least the 1.565 that we found in our random sample above. So draw a picture. Put your horizontal axis out there. Put your normal curve over the top of that. It doesn't have to be perfect, just draw a picture. The center of this distribution, our sampling distribution, is 1.50. So I'm going to put 1.50 at the center of this. Our standard deviation, or standard error, or the spread of this distribution, is the 0.0177. Now we're trying to find the probability of getting a sample mean that's greater than or equal to 1.565. So I need to be out here somewhere, 1.565. I'm trying to find the probability of being greater than or equal to that particular value for a sample mean. So how do we do this? Well, we can use the normal distribution in Excel, normdist, or we can use the standard normal table. Either way are going to give us the same value. So the probability of getting a sample mean greater than or equal to 1.565 requires us to do the 1 minus, because remember, normdist in Excel thinks to the left of the value that we put in for x. So we still do equals 1 minus normdist, just like we did when we did the greater than problems in the previous chapters. The x value that we enter now is this sample mean that we're interested in finding out the probability of. So our x is 1.565. The mean is the mean of our sampling distribution, so we put in 1.5. The standard deviation is where things really start to change in terms of what we plug in here. We need to plug in the standard deviation of the sampling distribution. So 0.05 divide by the square root of 8, because that's our sample size. So you can literally type this in, 0.05 divide by sqrt left parenthesis 8 right parenthesis, right into the box that asks for standard deviation. And then we continue to use true because we want to add up all the probability to the left of 1.565. Now when I did this in Excel, I found out that normdist is essentially 1. 1 minus something that's basically 1 is basically 0. So there's really a very, very small chance, practically zero chance, of getting a sample mean greater than or equal to 1.565. If you're interested in using the normal table to do this, then you have to convert 1.565 into a z-score. So that requires us taking 1.565 minus 1.5 divided by the 0.05 divided by the square root of 8. If you simplify that, you should get 3.67. So using our z-table, what's the probability of being greater than 3.67? Well, remember our z-table also thinks to the left. We look at the probability of being to the left of 3.67. That's basically 1. 1 minus something that's basically 1 is basically 0. So we get the same answer either way. We've assumed in that previous example that the population was normally distributed, which means that automatically the sampling distribution will be normally distributed. But what if the population is not normally distributed? Well, if it's not normally distributed, under some cases, the sampling distribution will still be normally distributed, or at least approximately normally distributed. That allows us to use normdist, which has all kinds of great properties associated with it. So if the population is not normally distributed, we can sometimes apply the central limit theorem, which says that even if the population is not normal, the sample means will be from an approximately normal distribution as long as the sample size is large enough. Okay, what does that mean? Well, we'll figure that out in a minute. The sampling distribution will still have that mean of the sample means equal to the population mean, and the standard deviation of those sample means equal to the population standard deviation divided by the square root of n. This is actually Theorem 4 in the textbook. This is the most important theorem in all of statistics. So we've got a population that's fairly skewed. If the sample size is very small, then we get a somewhat skewed distribution of all of those sample means. The central limit theorem says that as n gets bigger, our sample means will become more and more like a normal distribution, no matter how messy the population distribution is. So how large is large enough? For most distributions, we'll say a sample size of at least 30 will give us a sampling distribution that's approximately normal. In fact, for fairly symmetric distributions, n just needs to be greater than or equal to 15. So we're going to use the rule of n greater than or equal to 30 to be able to assume that the sampling distribution is approximately normal, unless we know that the population distribution is normal. If the population distribution is normal, then we know automatically that the sampling distribution of all of those sample means is also normally distributed. So here's a couple of examples just so you can kind of see this in action. We've got a uniform population distribution here. With samples of size 2, that very quickly begins to look like a triangle. With samples of size 5, that uniform distribution looks like a normal curve. Here's another example from your textbook. We've got a very skewed distribution. With samples of size 4, it starts to look bell-shaped. It's still skewed. You see that long right tail there. With samples of size 25, this distribution is bell-shaped and looks like the normal distribution. That central limit theorem then is going to allow us to say a lot of great things about the sample mean. Here's another example associated with using the sampling distribution. Suppose a population has a mean of 8 and a standard deviation of 3. And we've taken a random sample of 36 items. What's the probability that the sample mean will be between 7.7 and 8.2? Notice the difference in the way this question is phrased. When we would look at these kinds of problems in Chapter 6, we would see what's the probability of an individual item being between 7.7 and 8.2. Now the question is phrased, what's the probability that the sample mean will be doing something? In this case being between these two numbers. For this example, even though we don't know what the population distribution looks like, the central limit theorem applies because n is greater than or equal to 30. Our sample size was actually 36. Because of that, we know that the sampling distribution of all of those means must be approximately normal. The center of that distribution is at 8, and the standard deviation of the sampling distribution is 3 divided by the square root of 36, or 0.5. To find the probability between those two values, we can just actually use norm dist in Excel. So we would find norm dist of 8.2 with the mean of 8 and the standard deviation of 3 divided by the square root of 36, and subtract from that the norm dist of 7.7 with the mean of 8 and the standard deviation of 3 divided by the square root of 36. We could also convert these into z-scores. That 7.7 is a z-score of minus 0.6. The 8.2 is a z-score of 0.4. And we could use the z-table to help us find those probabilities. So the probability of being less than or equal to 0.4 is 0.6554. The probability of being less than or equal to negative 0.6 is 0.2742. So the total probability of being less than 0.4 is 0.6554. That's the whole area to the left of 0.4. We don't want this piece to the left of minus 0.6. That piece is the 0.2742. So we take the 0.6554, subtract out the bit we don't want, and we're left with 0.3812, which is the probability of being between this negative 0.6 and 0.4, or the probability of being between 7.7 and 8.2. Regardless of what the population distribution looks like, we know our sampling distribution is approximately normal because we have that sample size of 36, and that allows us to use the standard normal distribution to find the probability of interest.